So if I'm looking at this, we have to break it up. If x is positive, does the absolute value change it at all? So the absolute value of x would just be x, divided by x would be 1. Except I do have one problem here. That's when x is positive. Can I plug in a 0 in this? Can you do 0 divided by 0? No. So this piecewise, we're going to have to take off that equal to. You're just going to have if x is greater than 0 and if x is less than 0. Because if x equals 0, what happens to my function? It's undefined. Does that affect my limit at 0? No, because the limit doesn't care what happens at the point, just as you get close to it. So it's okay. It's going to have like an open circle on the graph when x is 0, but that doesn't change my limit. If x is less than 0, so the absolute value would make it positive. So that's like the absolute value of a negative would give you the opposite of x. When you divide by x, what do you get? Negative 1. Okay, so because I have different rules from the left and the right, we have to do the limits separately. We're going to do the limit as we approach 0 from the right. And the limit as you approach 0 from the left. If we approach from the right, my x's are greater than 0, so that means I have the first rule. So my function is just equivalent to 1. And the limit of a constant is the constant, so this is just equal to 1. If you approach from the left, you're plugging in numbers smaller than 0. So that gives us out negative 1. And the limit of a constant is a constant. Are those the same? No, we're getting two different limits from left and right, so they don't match up. So the overall limit at 0 does not exist. Questions there? One last piece that we need to talk about today. I did examples 9 and 10 yesterday. So if you have two functions and one is always smaller than the other, its limit is always going to be smaller than the second limit. We use this for what's called the squeeze theorem. Sometimes we may have a function that we can't do the limit of. Right now we can do the limit of a fraction as long as we can get the denominator to cancel out. We can do polynomials. But if I gave you something uglier that we didn't have any limit laws for, we couldn't do the limit of it. However, if we have two other functions, one that's always less than that one that's always bigger than that one, and if the limits of those two things equal the same number, then that means the middle one has that same limit as well. So this is called the squeeze theorem. It basically is a way of finding a limit of something ugly. And we're going to pick nicer functions to do that. We aren't doing a ton with the squeeze law this year. So my examples are pretty much going to be limited to sine and cosine. And those are really the only scenarios that I'm going to ask you to apply it to right now. So we'll do a few of those, and that will wrap us up for today. And this is just a graphical example showing you my pink G is always in between the other two, at least when you're near this particular x value. And so if the limits of h and f were equal, then the limit of g would have to be the same as well. So here's ours. Definitely can't apply any limit laws to this, can we? Do we even have any limit laws applying to trig functions? No. So we have to start from the ground up. I see a sine. What do you know about sine? What does it always fall between? Think about the graph of sine or the answers we get out on the unit circle. The values of sine always fall between -1 and +1. So we start with the very basics. I told you I'm pretty much going to limit this to sines and cosines, and isn't that true for both sine and cosine? So my first statement is what I know. No matter what, sine falls between -1 and +1. Now, I have to manipulate this piece in order to get the thing I'm taking the limit of. And we're going to do it step by step. If you change the angle on your sine, does that change the fact that it's still between -1 and 1? No. So what do I need to change this angle to? 1 over x. So this is still true if we make it a sine of 1 over x. Okay, what else do I need in here? X squared. So x squared is multiplied with the sine, so I'm going to take everything and multiply by an x squared. So that gives me -x squared less than or equal to x squared sine 1 over x less than or equal to a positive x squared. Okay? The next piece we need in this, we have a limit, right? So I'm going to add a limit to all three of these pieces. The limit as x approaches 0 of -x squared is less than or equal to the limit as x approaches 0 x squared sine 1 over x I do expect this much work, guys. You can't just jump from the original down to here. I want the step-by-step justifying it. Now, I still can't do the limit in the middle, but can we do the limit on the ends? Absolutely. That was from yesterday. These are just polynomials, so you can plug in. So if I put in, what is the opposite of 0 squared? 0. What is the limit as x approaches 0 of positive x squared? 0. So if this thing has to fall between 0 and 0, then we know it equals 0. And that's the squeeze law. Any questions on that one? all the ones we're doing are going to be very similar, so I'm going to do at least one more. We can do both if we need to, but we'll do at least one of these. So what's my first step? -1 less than or equal to sine x less than or equal to 1. Then, working our way out, we have to change our angle to match the angle we need. That doesn't change the -1 and the 1. Then what do I need to do? Multiply by x squared. And I guess I should have mentioned this in the last one. You have to be careful what you multiply by. If you multiply by a negative, what happens to your inequalities? They flip. But is there any chance x squared is a negative number? No. Now if it were like an x cubed, we would have to be a little more concerned because that could be positive or negative. But x squared is not a problem. We know that's positive. Okay, now what do we need? The limit. And that's good for us because we can evaluate the left and the right. This would be a 0. And that would be a 0, so we can say that overall the limit as x approaches 0, x squared sine of pi x does in fact equal 0. Questions on that one? This one is pretty ugly. Do you want to do it? Let's go ahead. Last example. Where do we start? Yeah, start with the sign. Sign is between -1 and 1. Next step, what am I going to do? Change our angle to 2 over x to match the problem. Alright, so I'm working my way out. We've got this much. What do I need next? I need that red. It's a square root, so is there any chance that thing is negative? No, so it's okay to just multiply it in. If it was something that would be negative, then you would have to turn around and do left and right hand limits. And it would kind of double your work. So if we do that, now what? We're missing the +1. So we're going to add 1 to every piece. Okay, now what do I need? The limits. This one is long. But you do have to show me every step like this. Okay. On the left and the right, as long as we get an answer that's defined, we can plug them in. So if I put in a 0 here, I get a negative square root of 0 plus 1, so that gives me 1. Over here, you get a square root of 0 plus 1, so that's a 1. So since those are the same number, I know the middle has to also equal 1. Any questions about the squeeze law? Okay, so that is our stopping point for today. The book problems are on your notes handout. Those are due Friday. We'll have a work day tomorrow. You guys know, just use the chat or send me an email if you need any help with those. Today's homework is a handout on Classroom, which would be due tomorrow, but I won't see you until Friday, so you'll turn it in Friday. And then you just have the rest of the hour to work.